All right, so last time we wound up talking about alkanes, specifically straight chain alkanes or unbranched alkanes, and we looked at a couple of different types of formulas, right? We looked at a structural formula, which is basically a Lewis structure. We looked at a condensed structural formula. Okay, which was basically looking at each of the CH3 and CH3 and CH2 units, right, as being entities of themselves, little blocks, if you will, like you might put together with Legos, right? You stick those together, they make these longer chains. We'll have a little bit of an addendum to that as we look at the structures of branched alkanes today. Just to make sure that we can specify what a branch is. We also introduced this idea of line angle formulas, and line angle formulas are probably the most useful part of or useful type of formula that you'll see in organic chemistry, because it allows you to draw really large structures very quickly, very easily. In general, we consider the ends and vertices of line segments to be carbons, and enough hydrogens are attached to those carbons until those carbon atoms have 4 bonds. And so what we're going to see is, as we get to branched hydrocarbons, right, we'll see where some vertices have either 1 hydrogen or no hydrogens also. So far we've looked at where we have 3 hydrogens attached to the carbons. And when we get to hydrocarbon derivatives, where we have some functional groups, like, for example, halogens or oxygen or nitrogen, we'll see that we're going to draw in those other atoms as well. So that's stuff that we'll see as we sort of move forward through the organic chemistry chapter. So far, we've looked at the first 10 alkanes, and that's really what you need to know, where we have the root of each of those hydrocarbons is what we underlined last time, right? So that's the root for 1 carbon long chain, or a root for a 2 carbon long chain, right? Meth or eth or prop or bute or pent. And so those are going to be things that we come back to, right? As we get to 6 through 10, hex, hept, oct, non, and dec for heptane, hexane, heptane, octane, nonane, and decane. And so those are going to be things that we need to know. Those roots are going to be used to describe long chains of carbon atoms. And what we're going to do is we're going to use those roots as we start to look at what are called substituents, or where a chain may branch off so that it's not all the carbons bonded in a row. And so that's our next step, is to introduce what are called branched alkanes, okay? So branched alkanes are what are considered isomers of alkanes. Okay, so isomers are just molecules with the same chemical formula, but different arrangement of atoms, okay? So in other words, when we talk about the arrangement of atoms, what we're gonna really look at initially are called structural isomers. And structural isomers are isomers where the atoms are bonded in a different order. Okay, so when we say a different arrangement of atoms, there are going to be different versions of isomers that are out there. A different arrangement of atoms means there's connectivity difference, okay? So atoms are bonded to different atoms than there are in different versions of them. And we're going to start out with butane as our example. But there's, again, it's a connectivity difference. And we'll actually see some different versions of isomers out there as well. In fact, there are different categories of structural isomers. There are also types of isomers called optical isomers, where the atoms are bonded in the same way to the same, at least to the same atoms, but there's a handedness to it, right? Like your hands, you know, they are mirror images of each other, but they're not superimposable, right? My thumbs wouldn't line up in this case. And so there's a handedness to some molecules as well, even though the basic structure is the same, right? The fingers are all attached to my hand, for example, but they're attached in such a way as to lend other properties to it. And that's something we'll explore a little bit down the line. Once we get to some more complex molecules, basically, we'll start to see that. When it comes to these structural isomers, what we've done so far in every one of the examples up here, what we could actually do to the name of those for the straight chain or unbranched alkanes is we could put an in front of it. Now, methane, you don't need to do it, or ethane or propane. But once you get to butane, now one of the ways we can specify that it's an unbranched isomer is put an in front of it. So it'd be in butane. And that specifies that it's a normal alkane, right? So in is going to stand for normal, okay? And that specifies that it's a straight carbon chain. Okay, so what we've done here is in pentane, okay, or in hexane, or in heptane, or in octane, in nonane, and in decane. Okay. So as we go back and go to our simplest of these structures that has the potential to have a branching, what we're going to do is we're going to look at in butane first. Okay, we're going to put it together in all of the ways that we did up above. So first off, we know that in butane, so isomers of butane are C4H10. The structural formula, or the Lewis structure, has 4 carbon atoms all bonded to each other, and those 10 hydrogens are bonded to all of the carbons. And then you've got your condensed structural formula, CH3, CH2, CH2, CH3. And you can write, there's some other condensed structural formula versions. This is sort of the most condensed version of the structural formula. So you can also write it in as CH3 and express the bonds between these CH3 and CH2 groups of atoms. Oop, and I'm totally stopped doing that as soon as I said it. Smooth, okay. CH2, CH3, okay. And so that's another way of doing a structural formula, but we also did these line angle formulas as well, where the line angle formula for butane is 3 lines where you have a carbon at the end of line segments and each of the vertices, and attached to those are hydrogen atoms, but we don't have to specify how many there are because we know, just because we know that carbon makes 4 bonds. But we can draw this butane molecule out in a different way, a different structure, okay? So in butane has all of the carbons bonded in a chain, but isobutane, which is the isomer of butane, it's really where the iso comes from, right? It says it's an isomer of butane, has a different, what we'll call a carbon backbone. Okay, and that's just showing how the carbons are attached to each other. So in this example, what we can do, and I'll try to show you with just a quick illustration of how we're going to take this apart. What we're going to do is we're going to go and change out, swap out this hydrogen here for this CH3 group of atoms. And we're gonna have a name for that CH3 group of atoms that we'll get to in a little bit, really not too far in the distant future when we start doing nomenclature. But we're gonna swap out those two things, which means our carbon backbone is going to change. And so if we look at isobutane, we're gonna have different connectivity of the carbon atoms. So carbon is gonna be bonded to a carbon, is gonna be bonded to a carbon, and the middle carbon is gonna be bonded to that fourth carbon. Each of these will have enough hydrogens to reach 4 bonds. So we should have, when we're all said and done, a total of 10 hydrogens. So there'll be 3 to any of those carbons that are on an end, or what are called terminal carbons. So a little bit more terminology for you. That's a terminal carbon. Right there. And in this case, that's a terminal carbon as well. So we're gonna have 3 hydrogens bonded to that one. This carbon in the middle already has 1, 2, 3 bonds, so it'll only be bonded to 1 hydrogen. And then the last carbon will be bonded to 3. So now we have, again, the structure. We have 1, 2, 3, 4 carbons, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And so this checks out as being a butane molecule. It has a chemical formula of C4H10. Now, this is, again, the Lewis structure for this. And so these molecules have the same molecular formula, but different structural formula. So this is the Lewis structure. If we were to do the condensed structural formula, the one with the lines showing how the groups are attached, we could have a CH3 bonded to a CH, bonded to a CH3, bonded to a CH3. Or if we were going to do that really condensed formula, where we don't even draw in those bonds, what we do is we say that we have a CH3 bonded to a CH, and then in order to illustrate that the CH3 that is branched off, okay, what we're going to do is put in a CH3 in parentheses off of or right after the carbon hydrogen in the middle. And then we're going to finish that off with a CH3. So as I change colors here, I can illustrate this a little bit more. So if we look at this piece as being a branch, right? It's branched off from the main carbon chain, right? That branch is going to be put into parentheses and sort of inserted after that particular carbon. And you know that that should be a branch because of 2 things. 1, it's in parentheses, but also 2, this says that these 2 carbons are attached, right? You know that this carbon is attached to that hydrogen and it's attached to this other carbon, which means that carbon has to be attached to one other thing. So the thing it must be attached to is that other carbon there, okay? And so when we go and draw out the line angle formula for this molecule, pen, there we go. So if we draw out the line angle formula for this, we can draw it out such that we do our initial 3 carbon chain. There's my 3 carbon chain, and then there's the branch, okay? And that's really all there is to isomers, except for they get more complicated as you have more atoms involved. And so with butane, there are really 2 versions of butane, right? 2 versions of this C4H10. There is the C4H10 that we call N-butane, and then there's this molecule here that we call isobutane. Now, isobutane is the common name, okay? There is another name out there, and we'll get into the naming in a minute, but there's going to be also what's called an IUPAC name. IUPAC, okay, name. And the IUPAC name for this is something we're going to come back and fill in after we do some nomenclature rules. And so what we're going to find is this IUPAC. It's the International Union of Pure and Applied Chemistry. Basically, a bunch of chemists got together and put together a list of names, right? And these are names that we've done when we've done nomenclature back in Chem 101, only we did that for mostly ionic compounds back then. Now we're going to start doing that for organic compounds as well. Okay, and we'll come back. Like I said, we'll come back and we'll do this, the nomenclature of this molecule in a minute. Okay, so all of the names for the isomers of pentane. Well, pentane is C5H12. So these are all the common names, okay? There are 3 isomers of pentane: N-pentane, isopentane, and neopentane. We've done N-pentane. So N-pentane has 5 carbons attached all in a straight chain with all the hydrogens attached to them. Okay. We can do the structural formula. Or the other version of this condensed structural formula. Ooh, those should be 2s. And then we have our line angle formula. Okay. And so there are all versions of or ways that we can draw in pentane. Now, I'm not going to force you to draw them in every single way, but you should be familiar with them and how to draw them in each of these ways. If I have you draw structures, I'll have you either I'll specify which type of structure you should draw, or you can pick one and sort of stick with that version of it. Now, when we go and change from N-pentane to isopentane, we're going to take this group here of atoms and swap it with the hydrogen on that first carbon, okay? And so when we do that, we can make what's called N-pentane. So I'm going to start out with the carbon backbone, C, 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 and C. And off of the second carbon is where we'll have our other carbon. And then we just fill in all 12 of those hydrogens around all of the other carbons. Okay. Again, getting kind of tedious here. Now, I want to point out something to you, however, before we go on and look at the other structures. This molecule, because remember, the Lewis structure doesn't tell us anything other than how the atoms are connected. This structure here is actually the same as if we draw it out like this, where that, oop, here we go, try this again. Come on, pen. My computer is being really slow right now. There we go. Okay. So we have our, in this case, the other way to draw this is with the carbon coming off of the second hydrogen. This will become, or excuse me, off of the branch coming off of the second carbon, either up here or down here. And what the difference is really just the direction that we wrote it, because we're going to find that the only way that this really differs is by flipping it around in space. And so when we have our rules for naming the molecules, we're going to find that the rules for naming the molecules will lead us to an easier way of determining if two molecules are the same or not. If you follow the rules for naming them, then you'll be able to determine that just by, by naming it. And so that'll make more sense when we start to look at the rules for naming these. Okay, so these two are the same, right? They may not look it right off the bat, but those two are the same molecule. One is just sort of a mirror image of the other. If you were to say, hey, you could put a mirror right here, right? And those two, set this one over there, right? They're basically a mirror image. And again, we'll come back and when we name them, it'll make more sense, okay? So the other versions, of course, are of drawing these, of these structures, are the first of the condensed structural formulas, CH3, CH2, CH, CH3, and then CH3, or CH3, CH2, CH, and then parentheses CH3, and then CH3 again. And our line angle is going to look something like that. Or like that. In either case, that little branch comes off of the second carbon from the end. Depends upon which end you're counting from, but that's part of the nomenclature that we'll get to in a little bit. Now, the way that we make the next version of this, okay, which is neopentane. So I'm going to go change my colors here again. And what you can do now is go back, if we go to isopentane, we can now take this CH3 on the end of the chain and now swap it with this hydrogen there. So we'll swap those two out to go and make neopentane. So neopentane now has 3 carbons in a row and then 2 carbons attached to the middle one. For a total of 12 carbons. Okay, so when we draw this the first of the structural formulas now, we've got a CH3, we've got a carbon now, and now we have 2 branches off of that second carbon, and they're the same. So we're going to call those CH3 with a subscript 2, and then we've got another CH3. Okay. And the other structural formula is CH3, bonded to C, bonded to CH3, bonded to CH3, and bonded to CH3. So we've got these 2 versions of condensed structural formulas. And if we draw out the line angle formula, it looks something like this. Okay. Now it doesn't really matter how those angles are or how they're oriented. That line angle formula, you kind of just want them to be at angles that aren't always straight lines, but you could, as long as you can sort of see that there's a vertex in the, or an intersection in the middle where all the carbons are on the surrounding atoms are bonded to the middle one, and then you've got terminal carbons all around that. That's how you draw that out. Okay. Now, before we move on and start to do naming, I do want to go back and illustrate one more issue with how we draw out the Lewis structures, with the understanding that we know that Lewis structures don't show us shape, they just show us what atoms are connected. Even if we have orientations that differ of the whole molecule, where we flip the molecule around. And so if I go back to that first drawing, we can draw those carbons and the carbon backbone. They don't have to just be drawn in a straight line every time. because the connectivity is the important thing. A carbon is bonded to a carbon, is bonded to a carbon, is bonded to a carbon, is bonded to a carbon. So they don't have to be in the same line. I could have a carbon bonded to a carbon, bonded to a carbon, bonded to a carbon, bonded to a carbon. That is still considered a straight chain because, again, the Lewis structure itself doesn't show the shape. So I have to draw in my hydrogens, right? But the carbons themselves are all bonded, one carbon to the next, to the next, to the next. Okay, so this is going to be an equivalent structure to what we've drawn up top in that Lewis structure. And just make sure we get all of those hydrogens in there, okay? And so in other words, if this Lewis structure here works, well, we could draw another line angle drawing. It could look like this, right? That's also an okay line angle drawing for this as well. Those are the same. Remember, all we're doing is depicting how they're connected, okay? So how is it that we know that they're the same? And that's where it goes back to what I've been alluding to and sort of previewing is the idea of nomenclature rules, okay? So nomenclature rules. We've got this set of rules that we're going to start with, and we'll add it in a little bit here and there when we need to. So nomenclature of alkanes. So we're going to give names to these alkanes, right? This is the IUPAC naming system. So the way we're going to do it, we're going to name the alkanes according to the longest carbon chain, okay? The longest chain of carbon atoms. So you can abbreviate it LCC so we don't have to write it down quite so much. The longest carbon chain, though, is going to be considered what's called the parent chain, okay? So for the first part of that, I'm going to go back up to our example of the isomers of pentane. I'm going to pick out a different color, and we're going to look at the longest carbon chain for each of these. So here's purple. Do this. So if I look at the first one, the longest carbon chain, I'm actually going to circle it here. Right? Here's my longest carbon chain. It is one long chain of carbon atoms. That's all I've got. But if I look at this, right, this is the longest continuous carbon chain, 1, 2, 3, 4, 5 for that first isomer of pentane. For the second isomer of pentane, right, I've only got 4 carbon atoms. So there's my longest carbon chain, 1, 2, 3, 4 in a row, and then there's a branch. However, it's not always that simple. I can see that I can also make this longest carbon chain in this direction, right, as well. As long as it's the longest carbon chain is the same number of length, I can set it up in either way. So for the first one, right, the longest carbon chain is 5 carbons long, right? So that's going to be a pentane. Okay, and so that's why it's in pentane. It's one long carbon chain. There's no branches off of it. The longest carbon chain for the second one is only 4 carbons long. So the longest carbon chain is a butane. Okay. Now you can see that we can count these carbon chains in any direction, right? I can circle one. I'll switch to a different color so that you can really see this. But I could circle another carbon chain here. I could circle. It's a little hard to see, I guess, but the yellow, I'm circling the carbon chain around there. Right, that would be a 3 carbon chain that would be a pentane, but that's not the one we're looking for because it's not the longest. The longest one is going to be the parent carbon chain. Okay. Switch back to purple color. Come on, pen. There we go. All right, so if I switch back to my purple color, you can see that I can get the longest carbon chain on neopentane this way. I can get it. Oh, I missed a hydrogen. I must have drawn it in and it didn't stick. Let me go correct that structure up there. There we go. Back to our purple. Come on, pen. So we've got our longest, we could have a longest carbon chain this way that was 3 carbons long. We could have a longest carbon chain that was this way, 3 carbons long. We could have one that was this way, 3 carbons long. So you can have these carbon chains that are the longest carbon chains that have a different route through that molecule, right? In this case, there are 6 different ways that you could potentially get a 3 carbon long chain, but that's still as long as it can go, right? So this longest carbon chain is 3 carbons, right? And so that'll be a propane. And if it helps, I'll put the number of carbons in each of these, right? Okay, so that's the first thing, is finding that longest carbon chain, okay? Now, this is, as we said, the parent chain, okay? The parent chain is going to determine the base name. So the base name is that butane or is that propane for isopentane and neopentane respectively. We're going to use that same ane suffix, okay? So that suffix will be something that might change. So it's still butane or pentane as the parent chain. When we switch to an alkene or an alkyne, right, which will have something to do with the number of double or triple bonds, then we can change the ending slightly, okay? But once you get that longest chain, the next thing you're going to do is see if it's branched, okay? If it's branched, you're going to assign numbers to that carbon chain, okay? So you assign numbers to the carbon chain, and you do so, as you can see here, in the direction that gives the lowest numbers to the carbon atoms with the attached substituents, okay? So basically you want to say, okay, well, where is an attached substituent? Where is that thing for that substituent, okay? And so if we go back up, right, this, or where is when I say a substituent, we're talking about the branch, okay? So that word there, right, is a branch, basically. It can also be a functional group later on. Okay, that'll make more sense when we get to functional groups, why you can call it a substituent, a branch, or a functional group. So it's we're going to number them based on the lowest substituent. So for our in pentane, we don't have to do anything else. It's just in pentane, it's pentane, okay? For our isopentane, right, we can number it in a couple ways. Now I'm just going to go over here and say, this is my substituent. And so the longest chain is going to be this one here, okay? So I'm going to circle that as my longest chain, and here's my substituent. Now I could have done it the other way, right? Because I can number it either way, and we'll talk about what the substituent names will be in a second, but we want to number it such that this branch has the lowest number. So you could number it going 1, remember we're numbering each of the carbon atoms, so 1, 2, 3, or 4. I could number it that way, or I can number it 1, 2, 3, and 4. And since the 2 here is greater than the 3, the way that we did it initially, that's not going to be the right way. It's going to be such that you give the carbon that branch is attached to the lowest possible number, okay? Now, if you have multiple carbons or multiple branches, you want to give as many of them the lowest, well, you want the lowest number first, and then if you have multiple that have the same number and then others, you're basically, long story short, you're minimizing the value of the numbers in that carbon chain where you have branches attached, okay? And we'll see examples of this with some isomers as we move through this stuff too. So we've now numbered it such that our numbering system is 1 there, 2, 3, and 4, okay? Then what we're going to do is we're going to take and we're going to set these up such that, so we're going to have hyphens are going to be used to separate numbers from the names of the substituent. Now, when we talk about the substituents, we'll get to that in a second, okay? Substituent names come next. We're going to use numbers and names And if we have more than one substituent, we're going to separate the numbers from each other using commas. So let's talk about substituents. Okay, so alkane substituents, so alkane branches, if you will. So we're going to use our base that we talked about, meth, eth, but, prop, etc., right, as a base for the substituents. For example, if I have something is bonded to a CH3, okay? Now I'm going to draw this little squiggly line in here to say that's some sort of a hydrocarbon. Okay? The other way I could draw this, also meaning hydrocarbon, is I have an R. R also means hydrocarbon, okay? The squiggly lines just says hydrocarbon. So in that case, CH3 bonded to that also. Anytime you have that CH3 group, that is called a methyl group. So M-E-T-H-Y-L, methyl. So methyl is going to be the substituent name, okay? If you were to have something like an R, some sort of a hydrocarbon bonded to a CH2CH3, that would be an ethyl, E-T-H-Y-L. So what we did essentially is this, is if you want to look at how you get the methyl, what you do is you take that methane and knock off one of the hydrogens and say, oh, no, that's now bonded to a carbon instead, okay? So you can sort of cross off, if you will. If you have a hydrogen here, right, you cross off that hydrogen, oh, now it's a carbon. And so that's part of, and that carbon is bonded to 4 other things somehow, okay? That's the whole idea. With ethyl, you take an ethane, right, which is 2 carbons long. Right, and you would knock off one of those hydrogens, and now it's bonded to another carbon, okay? It'll be a little different for propyl, but we'll look at 2 versions of propyl. So the R bonded to a CH2, CH2CH3. So the idea is the number of carbons in the branch is going to dictate the prefix used for the substituent, and the YL says that it's a substituent. It's part of a branch. So this will be propyl. Or if we were to instead, so you notice with propyl, right? We took that propane and what we did is we knocked off one of the end hydrogens there, okay? If, however, you take and you knock off the middle hydrogen and attach it from the middle, for example, so here's our propane molecule, right? If you were instead knocked off that hydrogen, it would become isopropyl. Basically, you're attaching it from 1 carbon in, it becomes an isomer. So you would have R bonded to C, H, CH3, 2, or R bonded to C, H, CH3, CH3. Those would be isopropyl. Okay. And so you kind of go through the list the same way, right? You say, okay, R bonded to a CH2, 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 CH3. That has 4 carbons, so that will be a butyl substituent. Or if you had R bonded to a CH, CH3, CH2CH3, that would be isobutyl. Okay, and so on and so forth, right? But going all the way through those those substituents, or through all of those in alkanes that we looked at before, okay? And so if we go back up here now, you're going to use hyphens to separate numbers, and you're going to use numbers from the names, and then you're going to use commas if you have more than one of a given substituent. So what we're going to do is we're going to place these substituent groups in order based on their alphabetical name, okay? So they're all going to be in alphabetical order. In other words, if I think about that, it'll be ethyl will come before methyl, which will come before propyl, right? And isopropyl will come actually between the ethyl and the methyl, right? Butyl will come before those, right? It's pretty simple and straightforward in terms of the name of the substituent and its ordering in the naming. But if you have more than one, right? If the same group appears more than once, okay? If the same alkyl group appears more than once, then the number of times that substituent is repeated is going to be specified using a Greek prefix, but the prefixes are not considered in the alphabetical order. So if you have two methyl groups, it would be dimethyl. If you have dimethyl, you need two numbers. And so we'll look at that for pentane here in a minute, okay? What I'd like to do is start out with the pentane molecules here. And what we're going to do is we know, so in pentane, right, is our IUPAC name, right? So the IUPAC name, right, is in pentane. Okay. If we look at the second one, though, we know that our longest carbon chain is butane. And right there, our substituent, our branch, is a CH3. So that is a methyl branch. Okay, so that methyl branch is coming off of the second carbon of the butane chain, okay? And so what we're going to do is we're going to put the number first. It'll be 2-methyl butane, okay? And so the number specifies where the substituent is, then you name the substituent, and where it's attached, and that's where the substituent is attached on the longest carbon chain, okay? If we go back to, or if we go to our next version now, and so I'll do this on a line angle drawing, assuming it'll let me draw a line angle drawing. There we go. So here's my line angle drawing. I'm just going to pick, we said we could number this in any way we want. I'm just going to pick to number it from left to right, just because that's how we always read. So 1, 2, and 3, which says that we have 1, 2 methyl groups. Okay. And both of those methyl groups are attached to this second carbon. Okay. But if I have 2 methyl groups, that says that I have dimethyl, okay? And so if it's dimethyl, then I have to specify the first methyl is attached to the second carbon, so I have a 2, but I have 2 of them, so I have to specify where the second one is attached also. It just happens that they're both attached to the same carbon. So it's 2,2 dimethyl propane. Now, if I had 3 methyl groups, I would have to have 3 numbers to associate with them, and it would be trimethyl. If it was 4 methyl substituents, then I would have 4 numbers separated by commas, and it would be tetramethyl. So that's how we're using the numbers and the prefixes. Okay. So with this in mind, we can go back and also name the isomer of butane. So we said that its common name is isobutane, but what we can do now is we can see there's a 1, 2, 3 carbons with a methyl substituent. So this molecule is 2-methyl propane. But in reality, you don't even need to specify that it's at the 2-methyl. It's really methyl propane. You don't have to specify that because there's only one place that one could be. So you wouldn't really need it. So methyl propane would be sufficient in this case, right? 2-methyl propane would describe where it's at, but the 2 is unnecessary in this case. That's kind of how we're going to name these things. And so when we get to more carbons, more chains, we're going to have more isomers that we can then name and specify. Oh, I did tell you one thing that I haven't done yet is how are those 2 up here the same? Well, remember when I start numbering, I have to number from the on the longest carbon chain, and it has to be closest to the side that would have that substituent. So this would be 1, 2, 3, 4. And so again, you would have a methyl substituent off of the second carbon, so that would still be 2-methyl butane. So it's all about how you number those chains in order to really get the right answer. And so your worksheet for organic chemistry gives you a lot of nomenclature, and so there's some fun things in there. Now the hard part of this is that sometimes it's hard to name these things. Sometimes it's hard to find that longest carbon chain. Sometimes it's not, but if it is hard to find, that you may wind up getting the wrong IUPAC name for a compound. However, just because you have the wrong IUPAC name doesn't mean you can't draw the molecule. Even wrong names can lead to right structures. Okay, and so your worksheet actually has some examples of that for some complex molecules. Okay, so let's go and look at. Wait a minute. So we've actually already done the IUPAC names for pentane, haven't we? Aha. So I'm a little ahead of myself in terms of slides. This is sort of the organizational aspect of doing this online for the first time. So we've already gone back and done the nomenclature for this, okay? So let's go ahead and, you know what? Why don't we go and get some more practice. Hold on, have it in here. Excuse me a moment. I don't see it in here. So we're gonna do some more isomers. We're going to do isomers instead of pentane. We'll do isomers of hexane. Okay, so you can disregard all this stuff. Okay, so with these isomers of hexane, what we're going to do is I'm going to do line angle formulas, and you can see we can draw these out in a variety of ways. And we'll name all of them. We've got 1, 2, 3, 4. 5 lines gives us 6 either vertices or ends of line segments. I'm going to take that carbon on the end and move it over to the second carbon over there. So my sort of systematically putting these together. So 1, 2, 3, 4 lines. There's 5 carbons. Here's 1 methyl group off of the second carbon there. I'm going to take the next methyl group and I'm going to take it off of the end there and move it over to the second carbon. So 1, 2, 3 lines gives us 4 carbons in a row with a methyl group here and a methyl group there. Then I'm going to take that methyl group that I just moved, I'm going to put it on the next one. So we've got 1, 2, 3, so 4 carbons, 1 here and 1 there. All right, so here we've got those are looking pretty good. Let's see. Yeah, so here are some isomers of hexane. And so you can kind of see this is a little bit of a game to play here, right? The first one is going to be in hexane. The second one, our longest carbon chain will be 1, 2, 3, 4, 5 carbons. And so this one has a pentane backbone with a methyl group at the second one. And so we have in pentane, we have 2-methyl pentane. Okay, so we've got 2-methyl pentane there. On the next one, we have 1, 2, 3, 4 carbons in our longest chain. We've got a methyl there and a methyl there.
Professor, do you mean hexane for the?
What?
We're doing hexane, right?
That's correct.
Okay. Oh,
Yes.
So, because
Right.
you took off the one and it turned into a methyl group, it turns into pentane?
That's right, right.
Oh, okay.
You're using that longest chain and then the other substituents. So these are all isomers of C6H14 here. Yeah, so that's what you're good. You saw that already, right? So the longest chain is the pentane, and here's the substituent. So the pentane accounts for 5 carbons, and the methyl accounts for 1 carbon. Okay, I'm missing one of my isomers, which I'll get to in just a minute. So we have 1 methyl. 2 methyls on the next isomer. And so here, both of those methyls are at the same position. So you're gonna have 2,2-dimethyl. In this case, it's 4 carbons long for the backbone. So it'll be 2,2-dimethyl butane. All right, so each methyl accounts for 1 carbon and the butane accounts for 4. Again, we have 6 carbons there. This next one, we number it. We can do it from either side. So 1, 2, 3, 4 carbons. And we have 2 methyls. Right, and so again, we have a butane as our parent chain, or the base chain. And so here we have now one of the methyls is at the 2 position and one of them is at the 3 position. So we'll call that as 2,3-dimethyl butane. And the one other isomer of hexane that we have has, instead of the methyl group being at the 2 position for the pentane, the 5 carbon long backbone, it'll be at the 3 position. So 1, 2, 3, 4, and that's where our other carbon will be. So here will be 1, 2, 3, 4, 5 carbons with a methyl group. And so this will be 3-methyl pentane. And so that's one of the things that it takes some practice doing this to start to gain an eye for how many isomers there are and what are the possible isomers for a given compound, and then also being able to name them. Okay? So that's where tomorrow's lab, again, we're going to get a lot of practice doing this in tomorrow's lab. You're going to have to just put together isomers and figure out what's the structure and what's the name for each of these isomers using the IUPAC system. Okay. One other thing, another thing to add to this is when you have, instead of just a hydrocarbon, right? If you have a halogenated hydrocarbon, right, this is going to be a hydrocarbon derivative. Okay, so a hydrocarbon derivative, if you have a halogen as a substituent, instead of, say, an alkyl chain, something like chlorine or fluorine or bromine or iodine, right? These substituents are going to be named in a slightly different way. Here we have chlorine. Okay, we're going to drop off that INE ending and it's going to be chloro. Okay, and that's going to be your substituent name. Instead of fluorine, okay, we're going to drop off the INE and it's going to be fluoro. Okay, similar to how we changed methane to methyl, instead of the YL, we have an O. Bromine becomes bromo. And iodine becomes iodo. Okay. So if we were to have a molecule like this, what that would just be as simple as saying, well, this is a methyl, or excuse me, that's a methane-based molecule, 1 carbon chain. So we've got methane, and our substituent is chlorine. So the first part gives us our chain, methane, and the second part, the substituent, is just going to be chloro. Okay, so it's chloromethane. This is all one word. Okay, if we were to take and say have something like CH3, CH, Cl, CH3. We don't need to use parentheses on this one because it's not a CH3, right? It's just one element there, right? As similar to how when we did naming of and structures of ionic compounds, when you had a polyatomic ion, you had to group all those together. Well, this is just a Cl, it's just a chlorine. You don't have to use parentheses to group it. So this would be, if we wanted to draw this out with the Lewis structure, it would look like this. And so you have a propane backbone, and you have a chloro substituent, right, at the 2 position. Okay, so it'd be 1, 2, 3. So it would be 2 chloro propane, which would differ from if you had CH3, CH2, CH2Cl. Oop, try that again. Right, which would be a chloro at the 1 position. Remember, we want to number from the side that would be closest to the substituents. So that's why I kind of drew it backwards for you. So that would be 1 chloro propane. So we use the same rules, right? And we use the same rules to number all of the substituents and find the carbon backbone that we did for the branched alkanes. Okay, so another one we could do if we had something like this, I'll do a line angle formula this time. Okay, so on here, you have at this vertex, you have a carbon here, but when you have substituents, you're actually drawing a line. If you have the elements here, right, this says you have a carbon chain that is 1, 2, 3, 4 carbons long. And since these lines end, right, these line segments here end with a letter, that letter specifies that it's not a carbon there, it's another element. And so what you have here, and there's a reason that I numbered from this side, the reason I numbered from that side is that the bromine is on the end there. So this would be, you have a carbon backbone, the longest carbon chain is a butane. You have a 1 bromo, and you have a 3 fluoro substituent. Okay, so when you name it, it would be based on the bromine being named first, because it's alphabetically going to be in place. And I'll do the sort of the reverse of this, if you will. So this would be 1 bromo, 3 fluoro, UORO, butane. Right, so the bromo comes first, the fluoro comes second. Even if we had done it sort of the reverse of this, we would still number from the side that would give us the smallest number. So 1, 2, 3, 4 in that direction. So our longest carbon chain is still butane. here we have a 1-fluoro and a 3-bromo. But the bromine will come before the fluorine, and so it'll be 3-bromo, 1-fluoro-butane. Okay? And so when it comes to nomenclature, remember, you number from the end of the longest carbon chain that has the nearest substituent, and then you name them such that they're named in alphabetical order with the number attached to that name, okay? And remember, if you have prefixes, those prefixes don't come into play when it comes to the naming, right? So these are all sort of examples of the various, at least chlorine, bromine, and fluorine. You could do iodine in the same way for these molecules for the nomenclature. Okay.
Professor, sorry,
Yeah.
quick question. So how come for the numbering, how come it stayed the same? Like, what, like 4, 3, 2, 1?
Yeah, so if you look at the two positions, so if we look at this right here, right? If this is my carbon that has a substituent attached to it, and this is the carbon that has a substituent attached to it, right? The one that's the closest to an end is going to be that has a substituent that's closest to an end is going to be your lowest number, right?
Okay.
So in this case, and in this case, it'll be the 3. So let me I can give you another example. Let's see, we're going to go up in this top corner up here to do another one. So if you were to say have something like this, or something like this. Yeah. So what you want to do is you want to say, okay, if I go to the first one, that's at the 3rd carbon, right? So I have a substituent at the 3rd carbon. It would be the 3rd carbon whether I started numbering it from the left or from the right. But since this one here, this iodine is closer to the right, I'm going to start numbering it from the right. So 1, 2, 3, 4. So this particular one, 1, 2, 3, 4, 5. I can't, get ahead of myself here. Number these, right? 4, 5. There we go. So this right here means we have a pentane longest carbon chain. We've got a 3-fluoro and a 2-iodo. Well, F comes before I, so this would be 3-fluoro. 2-iodo pentane. Okay. If I go to the next one, again, I can look at the position here and the position here, right? Well, the bromine is going to be at the 3 position no matter which side I number from. However, the chlorine, if I number from the right, the chlorine would be at the 4 position. If I number from the left, the chlorine would be at the 2 position. Well, that means I'm numbering from the left because 2 is smaller than 4. So we have 1, 2, 3, 4, 5. And so this molecule will be, again, we're going to number them from the end that has the closest substituent, but we label them, or when we write the name, we put it in alphabetical order. So it'll be 3-bromo, 2-chloro, pentane. Does that answer your question, Nora?
Yes, thank you.
Okay. Okay. So I think, yeah. So what we'll do, sort of to wrap up today, we're gonna got 2 more things that we'll cover, and then we'll call it for the day. The next thing is when you have a cycloalkane, it's a cycloalkane. If you think about a cycle, right, a cyclic structure, something that's a circle, right, would be a cyclic structure. And so when you have a cycloalkane, it's going to be when a chain contains 3 or more carbon atoms, okay, first and foremost. You can't have a circle without at least 3 pieces attached to it. But those atoms are going to join together to form a ring or a cyclic structure, okay? So you can think about a ring, right? Cyclic. So the way that we can do that is we can have carbon bonded to carbon, bonded to carbon, and then the chain itself is attached. Now, when you have a cyclic structure, this is going to have a different formula. It's not going to be just a simple alkane. It's a cyclic alkane. And a cyclic alkane, right, you still have hydrogens bonded. Each of these, they're cyclic alkanes because they're still carbon, each carbon is bonded to 4 other atoms. So they're all single bonds still. Okay, so that's your idea. That's the idea here. They're all single bonds. However, now you have this ring structure introduced. And this carbon this carbon ring has 3 carbons, right? So it's based on propane, right? Only since it's a cyclic structure, we're going to call this cyclopropane. Okay? And so the cyclo says, oh yeah, I don't actually have propane. I have cyclopropane. The structure or the chemical formula of propane, right, the C3H8. Almost did it again. Okay, so propane is C3H8. So carbon, carbon, carbon. Here are all my hydrogens. So in essence, what I've done is taken that hydrogen and that hydrogen, got rid of them, and attached these in a ring, right? Attached this carbon over here, right, on one end to the carbon on the other end to make it a cycle. So when you have propane, it's C3H8. When you have cyclopropane, right, cyclopropane is C3H6 because you've essentially lost, right, those 2 hydrogens where the carbons decided to stick to each other, right, the ones on the end. So if you go and get now 4 carbons that are bonded together, in a ring structure, right, this is based on butane, only it's a cyclic structure, so it'll be cyclobutane. And by the way, we can draw these with line angle formula as well. So cyclopropane's line angle formula is a triangle, right? All of the carbons are at vertices. Cyclobutane is a square. If you wanted to do cyclopentane, right, you'd have a pentagon. Right, and so cyclobutane will be C4H8, cyclopentane will be C5H10. And then sort of the last of these that we'll look at right here is going to be cyclohexane. All right, so cyclohexane, right, has 6 carbon atoms in a row. It's C6H12. Now remember, if you remember the bond angles for a methyl or a methane rather, carbon likes to make tetrahedral molecule shapes. So the bond angles tend to be around 109.5 degrees. But you can see that the bond angles in cyclopropane that bond angle there, right? That's like more like, 120, or sorry, that's a 60-degree bond angle, right? 60-degree bond angle is not exactly a good thing for the stability of that bond. It turns out cyclopropane is a fairly unstable compound. It actually will do what's called isomerizing to form a molecule called propene. Cyclobutane is also, if you think about that, right, that's a 90-degree bond angle. That's also going to be a fairly unstable compound, right? And so what you wind up with when you have these cyclic alkanes is something that they call ring strain. Basically, because of how the angles of the bonds, right? You have weak overlap between the bonding orbitals. At least you have that until you get to cyclopentane. There's less ring strain there. Okay, so you have less ring strain there. And then in cyclohexane, it turns out that cyclohexane adjusts its shape in such a way as to minimize any potential ring strain also. And that's something, if we get to it, we'll talk about it. It's not something that I'm really gonna drive toward getting done right now. It's something that if we get to it, it's a bonus, and if we don't, we don't. But it's neat to understand that, hey, these bond angles actually matter, right? You can lock these carbons in place to give you that 60-degree or 90-degree bond angle there. It's just not going to be a very strong bond, and that can lead to extra reactivity for those molecules. Okay. And so with that, we'll end there. I'm not going to go into the reactions just yet. We'll talk a little bit more about reactions tomorrow, and then we'll do some more isomer work. And we'll get, and then of course we'll cover some more material on Thursday, take our quiz. We'll get through most of the rest of the stuff that we need to cover in chapter 22 by the end of Thursday. So we should be finishing up 22 if we're not done with it, and starting in on 21 on Monday, or at least getting a little bit of that in there. So our next exam next week is going to be chapters, 18, 20, no, 22, 17, 18, and 22, okay? And so we will end our lecture there for the day, and I'll try to take questions if